Okay, I'm going to try to wrap this up, but looking at it, there's tons. There's 14, 15, 16, 17, 18, 8 graphs, 19, 20, 22, 23. So it looks like this is going to be another multi-parter, especially since I seem to take my time and get bogged down. But you're going to get these questions here that are all related to functions. Okay. Okay, let's see if I can do that. There we go. Crop, zoom in. Let's try to grab 2 of them at a time. Here we go. And there we go. Low and high blood pressure can both be dangerous. The doctor uses a special index, PD, to measure how far from the normal blood pressure is, and the equation in a sense sort of an absolute. This makes sense. So 80/120 is blood pressure, and it's clear that the middle point of this is 100. So when you're 20 up above or 20 below, it's fine. But anything in excess of that is considered the start of high or low blood pressure. And this is called, I think this one's systolic and this is diastolic. It's when the heart pumps out blood, and then this is when it doesn't. So the pressure is supposed to be lower. And P here is this normal systolic blood pressure. Sketch the graph of this index, assuming that normal systolic blood pressure is 120. So that means this P here is 120. And P is, let's see. Let's read it again. Low and high blood pressure both be dangerous. Doctors use a special index, PD, to measure how far from normal the person's blood pressure is. The equation PD is equal to the absolute value of P minus P bar. P is a person's systolic blood pressure, and P bar is the normal systolic blood pressure. Sketch the graph, assuming that the normal systolic blood pressure is 120. So that would really mean this. PD, and I can see, let me just shrink this because I can see that I've actually got a huge graph going on here. Down to there, and crop, and do that. There we go. Let's try this. PD, I'm still going to make it bigger. Try that. It's going to be equal to the absolute value of, we'll use a straight up, I'll do it in a bit, P minus 120, like that. And it's the absolute value. So I want you to notice something. Just make sure I got it right. Okay. So, as I punch in P, this is the same as Y, and this is the same as X. So as I punch in values of X, I take the absolute value of it, and I get a Y. Now let's pretend that P was 120 in here. Well, obviously I'm going to get 0 in the diastolic. Right? It's going to result in 0. So you can do a little T-cell graph to see what various things you get that are, you should use 120 because it's clear if I look at this in terms of an absolute value graph, if I phrase it like this, this is a absolute value graph that's been displaced 120 to the right. Okay? So that means I would have a graph like this. And down here, I should expect 120, 0 as the vertex. Okay, let's see how I can figure that out. Well, I can see 120 has an impact, so I should probably make a T-cell like this of just X values. If I want to do it old T-cell value. Now, it's clear that if I put a 120 in there, I get 0, and the absolute value is 0, 0. So let's take values just around 120. If I take 115, 115 minus 120, is minus 5, but then it gets absolute valued 5. If I take 125 minus 120, it's 5, and then it gets absolute valued, which is 5. So I'm going to notice this pattern that even though this one's below 120 and this one's 5 above 120, the result, because it gets absolute valued, is 5. And you could pretty much construct an endless chart knowing that, like this. So, for instance, I know this is going to be 10 apart, and so it's going to be that. And I can even do, down below, I can do 130. It's going to be 10 apart. and 140 is going to be 20 apart, and so on. And up above, I can do the same thing. 100 is 10 apart, which means that, like I suspected, if I'm going to graph this graph, way over here is the vertex, and I'm going to discover it's this value. And then it's going to go up like this, and down like that. And everything on this side is going to be 5, 10, 15, 5, 10, 15, just like this. So 100, 10 is up here. 100, 10. 110, 10 is going to be here. 10 over here. And so we can even use Desmos to help us out a little bit on this one, because this is not a huge issue. So I'm just going to close all these. So if you look at, you can even do PD, or P3 is equal to absolute value of P1 minus 120. And sure enough, we can go, we'd have to really see 120 over here. Let's go 100 to 120. And we can see it right there. And we can even pull up a table of charts, or a table of values, based on this. So let's see, can it handle it? Now let's just put that right in there like this, and it should be able to handle it like that. There we go. And will it label it for me? Doesn't look like it's going to label it. We'll just do minus, we'll go 5 at a time. And we'll see if we can see those points. There should be one there. And I'll just make this y is equal to x so that we can maybe see some points. Still can't see some points. But if that's x and that's x, will you show me some points? Still won't really show me some points. Anyway, oh yeah, sorry, it shouldn't be 110. It should be 130, 125, 120. That's why I can't see them. 115 and 110. So there we go. There we go. There's the points I was looking for. So it'll look like that. So this would be considered normal, and then as we get off, we're getting into danger zone. And then they use this y value over here. They'll use the y chart to determine how bad your blood pressure is. So as you start creeping 10, 20, 10 is like mild, 20 is moderate, 30 is severe. And they adjust your medication based on that. Now that's a really rudimentary thing, but that's kind of pretty much how they measure blood pressure. It's always a distance from normal. They wouldn't necessarily use an absolute value graph, but anyway. So we have a guy who uses the relationship times equal to distance over speed. By the way, that's very true. If you look at the relationship, distance over speed or velocity, depending which one you're doing, is distance divided by time. I'd like you to learn this very valuable triangle, whereas if you put the numerator of any fraction that has a situation like this, where something is equal to something divided by something, and you put it in this little pyramid structure like that, divide off the top, divide off the bottom, you discover you have the formula for anything. Distance is equal to time, velocity times time. Time is equal to distance divided by velocity. And velocity is equal to distance divided by time. So that's a fantastic little tool. Whenever you have a formula that's something is equal to something divided by something, put it into this pyramid and you'll now have a formula for anything. In this case, he's saying time is equal to distance over speed, which is true. Time is equal to distance over speed, to plan his kayaking trip. Tomorrow he plans to kayak 20 kilometers, which is a distance, across a calm lake. So let's start by doing this. You can think of it as, there he goes, you can see it's right over here. So the time based on the speed is equal to, he's going to fix the distance as 20, divided by whatever time he takes in seconds. So depending on how long he takes, sorry, depending on S is a speed here, depending on what speed he goes, as this goes up, time goes down, right? Because we learned from fractions, as denominator goes up, the result of this goes down. As this goes down, the result of this goes up. So the higher the speed, the lower the time. The lower the speed, the higher the time. If we were going to graph it, yeah, there we go. Okay, so if we were going to graph the first one, we can see that really this is no difference than a y is equal to 1 over x, right? Multiplied by 20. So a y transformation, a y stretch of a factor of 20. And you might say, hey, well, why would we have that? Like, it's going to look like that. And then it's going to look like this. What the hell is that? Well, when you do real case scenarios, there's only such a thing as positive time and positive speed. Well, there's technically negative speed, but there's no such thing as negative time. So this side of the graph is ignored. It's only this side. Now, when we multiply 20, well, what do we know about a point on here? It's 1, 1. When we multiply that y value by 20, because that's what that 20 means, we get 1, 20. So we don't have any vertical or horizontal translation. We just have a very stretched 1, 20. And if you want to put in a couple variables, like for instance, what happens when my speed is 20 kilometers an hour? Well, my time becomes 1 second, right? So when speed is 20, it's 1 second. So I got this nice little dot here, 20, 1. Speed of 20 results in 1 second. Or is it in hours? Kilometers, time based on speed, kilometers per hour. So it's hour. So if he goes 20 kilometers an hour, it will take 1 hour, which makes sense if he's traveling 20 kilometers distance. So you have 20, 1 as a point. And then as an example, if I take 1/20th of a speed, so if I go 0.2 kilometers per hour, I will get a time of, well, let's think of a better one. When x is 2, time will be 10 hours. So when I'm going 2 kilometers an hour, it'll take 10 hours. So I'll have 2, 10. So that means I have this, I can pretty much do a T-cell like this. Again, just take some values. So remember that x is his speed and y is his time. So you'd actually use the thing at the right. And I can just right away say, well, when x is this, it's going to take me an hour. If x is this, it's going to take me 0.5 hours, right? And now let's take some smaller times. When x is 0, it can't be, so let's just take x as 1. And it's going to take 20 hours if my speed is 1 kilometer an hour. What about if x is 0.1? Well, that'll create 200. It'll take 200 hours if I go 0.1 kilometers an hour. So we can see this little divergent thing going on, especially 1 to 20 and 20 to 1. And so there's probably a midpoint in there, right? Now what happens when x is 10? We get a time of 2 hours. So it's clear that's the crossing point. So if we look at it, 0.1, 200 is way up here. 120 is like here. 10, 2 is like there. 20, 1 is like there. And 40, 0.5 is like there. So you get that thing right there. And you should label all your points. And that's one way you could see it. Now what happens in the next thing? The next day we'll kayak 15 kilometers up a river that flows at 3 kilometers. So that means even though he's going 15, he's going a speed this way, he's got a flow against him 3 kilometers. So the interesting thing about speeds, if I'm going 20 kilometers an hour in a canoe this way with a 3 kilometer an hour backflow, I'm going 17 kilometers an hour. If I'm going 20 kilometers an hour this way with a river flow of 3 kilometers with me, my net speed is 23. So you can actually add up or subtract speeds that are along the same plane like that. So that's what he does. In this case, his distance has changed to 15, so that's changed from 15. And his displacement goes all the way to the right by 3. So 3 becomes this. Right here. Goes 3 to the right. So I would take all my original values, and instead of multiplying them by 20y, which by the way is what happened there, I would multiply them by 15 on the y's, and I would add 3 to all my x's. So again, for that, it would help to take a couple of the parent graph, just to show you what the point of this is. And the parent graph is 1 over x, right? 1 over x. So I'll just show you what happens when x is really small, which is 2.1. Y is 10 times bigger. And actually we'll do this. Doom. When it's 0.1, 10. When it's 1, 1. When it's 10, 0.1. And when it's 100, 0.01. All makes sense. Now let's look at the first translation where I take these same y values and I'm just going to be multiplying them by 20. So I get all the same x values. And then I just take all the y values and multiply them by 20. Pretty self-evident. And then for the next one, I take all my y values, and I'm going to sort of ignore the negatives. You could do the negatives as well. I'm going to take all my y values. So this one was 20 over x. And this one is 15 divided by x minus 3, essentially. That's bad. It's essentially 15 over x minus 3. Like that. So instead of figuring out those numbers like I did here, I would just multiply my y values by 15 and add 3 to all my x values. So my x values are going to become this. And my y values are going to become this. And I can just plot them. So instead of plotting them, I'm going to pull up 3 graphs. There we go. Here's the parent graph. Here's the vertically stretched graph. And here's the less vertically stretched translated to the right by 1. I also want to put up the new asymptote there. And you can see it's the only one that's asymptote has changed. And really we're only looking at things that happen to the right of the asymptote. So you'd only ever study this part of the asymptote, rather. We don't care about the negative world. So we'd only study this. So let's see if we can find a couple of the values. I'm looking for 3.1 and 150 would be a good one. Let's draw a line straight through y is equal to 150 to see where we cross. Whoop. Yeah, I got to choose the right one. I'm really looking at that. There you go. 3.1 comma 150, just as anticipated. What's another one? At 15, I should see 4. So at 15, I should see 4. Let's see. There it is. Oh, I had it too. 4 comma 15. And at 13, I should be see 1.5. Just keep getting it and losing it. There we go. 13 comma 1.5. And finally at 103 I should see 15.15. So it's way back over 3. And if you want to see it more accurately, just draw a line x is equal to 103. Zoom in and you should see where it crosses. 0.15. So you can see all those translations worked. You'll discover the same thing for this graph in here in blue, and of course the right side's the only part that simulates the canoe because negative time doesn't exist, negative time and speed. So you'd put the same restrictions on the x. You'd make x is bigger or equal to 0. So that's the only part of the graph that we care about. And looking at some of the translations, if I draw a line through y is equal to 2,000, 222 and 0.2, I'll see all the spots I was concerned about. We'll do 222 and y is equal to 0.2, and we'll cross each of those. So if 0.2 is supposed to be 100, so we'll go over to 100. And make sure I have the right graph on. Oh yeah, it's not supposed to be 100. It's supposed to be, when x is 100, sorry, yeah, 0.2. I should see x at 100. So let's see what happened there. Y is equal to 0.2. Did I get it right? No, I got it wrong. I didn't translate my yeah, that should be 0.02 for that one. And this one should be 0.2. So this one should be up 1. So multiply all my y values by 20. No, that should be 2. So 10, I should see 2. Let's use the x values instead. Be a lot easier. So the x values I'm looking at are 0.1, 1, 10, and 100. Let's see where that crosses. Still didn't cross there. Where's it supposed to cross? At 200, okay. There it is. Would have been easier to just draw y is equal to 200 and find it. Right there. Now let's try y is equal to 20. One comma 20. Did we get it? Yeah. And y is equal to 10. We should see the point 2 comma 10, and or 10 comma 2, or what did I get wrong there? Oh, I keep punching in the, should be y is equal to 2 there. There we go. 10 comma 2. Notice that there's that sort of relationship on the other side, and the middle point of this should be there. And when you think about it, the middle point of this, yeah, gets multiplied by 20, so it's 20 comma 1 way over here. There it is over there. But this middle point right about there, where the numbers should, I think the numbers should match. And I should be able to spot it by drawing y's. I should be able to spot it right there. Yeah, so there, the numbers match right there. That would be essentially the middle point. I wonder what the formula would be. How will these numbers, when will x equal, so for this one, I think, so when are the numbers going to match? When you have this. So, we've pretty much figured this one out. When will these numbers match? When I've multiplied something like this, where y is equal to x, when will the x and the y values be the same? Well, when they're equal, right? So you could just do this. X is equal to 20 divided by x, which means x squared is equal to 20, which means x is equal to the square root of 20. The square root of 20 is 4.47, which means, explains why that is sort of the symmetry point. So that's interesting. So the square root of the y stretch, if there's just a y stretch, should be the focus point. Let's see if that's true for the other one, which was like this. Kind of abstract what I'm doing here, which was this one. So in this case, I'm pretending both x's are the same. I multiply by x minus 3. I get x squared minus 3x minus 15. And then I would solve that, which is, let's see, plus 5. I'd have to use a quadratic function. And I'd have to use 1 minus 3 minus 15. Okay. And I get at 0.565 and negative 265. So that's where the x and the y coordinates should be the sort of middle point and matching. So let's see if that's true. If you don't know what I'm talking about, that's fine. This is just me going on a little too crazy. We'll get rid of that. Get rid of that. Get rid of that. Get rid of that. So according to me, I should see 5.6533 comma 5.65333. I'll just draw a line is equal to x minus 3 to find it. Should be there. Almost. That didn't work. Nope. So let's just try to find it instead. Y is equal to 5.6. 5.63. What was it? 5.65331. Yep, those points are identical, but it doesn't really mean they're symmetrical. So that's how, because it's been distorted and translated so much. So that's not actually the symmetrical point I was looking for. I was looking for something over here. So that's just the 2 points that are equal, but because this is distorted 3 to the left, that is not a valid way of finding the symmetrical point. And I believe the valid way of finding it is drawing not the line y is equal to x through it. Let's bring that graph back. Not drawing the line y is equal to x through it, but rather drawing the line x is equal to minus 3. Yeah, there we go. That's the symmetry point. They don't match, but that's definitely a symmetrical point. Interesting stuff. So that's like the reflective point, I guess. Hard to explain what I'm going for here. You can see it's equally matched on this side and equally matched on that side. And that line matches that displacement or that translation. Anyway, so you can see where I go on and on and on and easily get distracted. Okay, so then they want you to practice the wording of it. Like this. So if it's reflected across the x-axis, that means there's a negative in front of the y. So you start with this. and you list all the things. So reflection y-axis means put a negative at the x. Stretch vertically by 3, so put a 3 in front. Translated 5 units right, put an x minus 5. And 2 units down, just put a plus 2. So there's two ways I can write this. I can write my transform function like this. And put a big old square root like that. Or I can write it like this. Which says take the f function and alter it in the same way. Draw the graph. Well, okay. Multiply all your y values by 3, then add 2. Multiply all your x values by minus 1, and then add 5. And then draw the graph and the original function you're working with. And there's a lot of graphing, so indeed I could say learn to graph. Okay, go with 1, 1. Close that, zoom in. There, that should do it. Put it on your paper. Take your rules. Take your standard points. Standard points for a square root function are 0, 0, 1, 1, 4, 2, and 9, 3. And so I'm going to reflect it in the x-axis. So that means if I'm going to multiply, I should just look at this one here. There we go. Instead, I'm going to multiply all my y values by 3 and then add 2, my y values. So I get 2, 5, and then they should go up by 3 after that. 8, yeah. Then it should be 11. And then all my x values, I'm going to multiply by negative 0 and add 5. So this first one's 5. Negative 1 add 5, 4. This next one, negative 4 add 1. And negative 9 add 5, minus 4. So now I have the points. And this should be my vertex. So 5, 2, right there. Now remember, it's reflected in the y-axis, so it's going to go that way now. And then 4, 5 up there. And then 1, 1. Whoa, that's weird. 4, 2, sorry. 4, and it's 5, 2, 4, 5. Yeah, there we go. 4, 5, 1, 8. And then minus 4, 11, which is just about there, just above, right there, which means I got something that's going like that. There we go. So notice that the vertex has indeed moved 5 to the right and 2 up, which means the range is y is bigger or equal to this, 2. And the domain is y is smaller or equal to the positive of that, 5, because of this reflection. It goes that way. So let's see if that's true in the graph. Minus 1, minus 3, minus 1, minus 5, plus 2. Forgot it already. And there we go. Oh, what did I do? Oh, I put this in the brackets. There's no brackets there. Brackets should be closed right about there on the outside. Right there. There we go. So there we go. 5, 2. And let's see if I can just pull up some values. So 5, 4, 3, what were some of them? 1 was one of them. 4 and 9. Is it minus 9? No. Sorry, 5, 4, 1, and minus 4. There you go. Those are the 4 points. And sure enough, flow stretch vertically is translated to write the equation of the new functions. Okay, and I'm not going to graph that one. And I might just cut down on the graphing just to save time. Okay. So the new function, g of x, is equal to 3 f x plus 1, because it went 1 to the left, and then plus 2. Stretch vertically, yep. Oh, it's reflected in the y-axis, which means there's also a minus here. Stretch by factor 3, translated 2 units up, and 1 to the left. There we go. So that would be it. Match. Okay, so this should be easier than it looks like. Okay, so I'm gonna teach you some quick ways to do these on a test. Okay, so first of all, before you ever freak out on it, I want you to say, okay, what's the parent function of the thing I'm looking at? What's the parent function? There we go. Because it can save you a lot of time. Okay, so if we look at this one, that's a 1 over x, and that's a 1 over x, and that's an absolute, and that's an absolute, that's a square root, and that's a square root, and that's a parabola, and that's a parabola. Let's focus on the parabolas, because this will have a vertex of minus 4, comma 1, and it'll be facing down. Minus 4, comma 1, facing down. So right away I can go b, and this one will have a vertex of 2, comma minus 3, and facing up. 2 minus 3, because look, the units are in 2 and in 2, which is there, and facing up, so that's g. Easier to spot. Now these are square root functions. Now the nice thing is they're both going to be facing curving up, and they don't have a x reflection, so that would have made it easier. However, they do have a vertex of minus 3, comma minus 2. So let's find the one that looks like minus 3, comma minus 2, which is that one, which is A. So this one is A. And, sorry, this one is A. And I know I'm not quite marking it well, but you get the idea. And this one will have a vertex. This is expressed incorrectly. There is a reflection there. So that's minus x plus 1 in the brackets, minus x plus 1, and when I take the minus out, it becomes x minus 1, which means its vertex is 1, comma 1, and it's a square root function. And it'll be facing left and downwards too, because it has a minus in front. And that's this one, 1, comma 1, so that's h. Then these are absolute functions. That one's facing down and that one's facing up. That's pretty easy. So this is the one facing up, so that's an E. And that's the only one facing down, which is D, so that's a D. Then you're just left with these. So this creates a reflection in the y-axis, so you won't really be able to tell much about it. And this creates a reflection in the x-axis, so they'll both look the same in terms of reflection. But this one has a coordinate of a sort of the asymptote will be at x is equal to 2 and y is equal to 1. And this one only has a y is equal to minus 3. So right there, there's the y is equal to minus 3. So this one, E, belongs to graph F. And that only leaves one left, this one, but you can see that the asymptote of x is equal to 2 and y is equal to 1 is right there. So that one belongs to C. So really the secret is to start with the ones that you know have vertexes and spot those. Then look for asymptotes, or look for the things that easiest define it. And also look for trickeries like that where the thing is not factored correctly. Because that'll instantly tell me that that one is this one. Okay. Okay, so they just want you to learn how to recognize which one's A and which one's F and all this other junk. Okay. So we're going to just label them, right? A, K, D, because we're going to leave the minus there, and C. So if it's a vertical stretch of 2, that's 2. The reflection in the x-axis means it's minus 2. A translation 4 units to the right means D. So if it says minus D, it's just going to be 4. But if I'm going to explain it to you, it's going to look like this because it's 4 to the right. But because they have the minus right in there, I would just say D is 4, right? Because the minus is part of the equation. And then are applied to this. So do they want me to they want me to sketch it? I'll forget that. Anyway, translation 4 units right applies to the square root function. Okay. So the only thing that happens there, yeah, not much. That and that. So we're talking about x minus 4. So the only thing that happened, 0, 0 is then usually the vertex, and this is now 4, 0. So we're going to have this at 4, 0. And the only thing that it's going to happen is I multiply all the, I would add 4 to all y units, x units. So 1, it's actually going to be 5. And normally this is 1y, and when I multiply by minus 2, so it's going to go like that. It's going to be 5, minus 2. And then the next one would be 4, 2. So when I add 4 to it, it becomes 8. And 4, 2, when I multiply by minus 2, becomes minus 4. So it's going to go like that. And keep going like that. Now, the domain and range is dictated by the vertex. So y, the range of this is y is smaller or equal to 0, and x is bigger or equal to 4. Because the square root function is going to look like that when it's reflected in the x-axis. So the range now goes down. Okay, this next one is a reciprocal. And a vertical compression by a half. So that means A is equal to half. A reflection in the y-axis means K is going to be negative. Translation 3 to the left means D is going to be minus 3 to make it. Well, essentially in that bracket, it's going to be x plus 3. That's the problem with using just the minus. If I'm going to tell you what D is to create that, D is minus 3. And that's where your teacher might, it's really confusing when you put it like this. And a translation 4 down means C is minus 4. And so what does that mean? It means the 3 left moves the asymptote x is equal to 3. And a translation 4 units down moves the y asymptote y is equal to minus 4. It would also mean you're going to multiply all your y values by a half and all your x values by minus 1. By minus 1, yeah. So that means normally my 1 minus comma 1, which is normally here, is going to be a half times minus 1. It's going to become a half and minus 1. Then I'm going to add, it's going to become minus 1 comma half. Then I'm going to subtract 3 from that, so it's going to become 4, and I'm going to subtract 4 from that, so it's going to become negative 3 and a half. So then my new point here moves over here to like there. My asymptote becomes x is equal to minus 3, and my x is equal to minus 3 like that, and my horizontal asymptote becomes y is equal to minus 4. So that means this thing's going to hug this like that, and hug that like that. And I'd add a few points. What's the domain and range? XER, but x cannot be minus 3. YER, but y cannot equal minus 4. A horizontal compression by a factor of a third. A vertical stretch by a factor of this. Translation 1 unit right, translation 6 unit down are applied to the absolute value. Okay. Horizontal compression, let's skip that for now. Okay, well actually no. K is equal to 3 then. A vertical stretch by a factor of 3. A is also equal to 3 then. Translation 1 to the right. So in that bracket it's going to be x minus 1. So you could say that D is equal to 1. And then finally translation 6 units down. So C is equal to minus 6. And I think that's all of it. There's no reflection. Now the absolute value normally has a 0, 0 vertex. But by moving it 3, 6 down and 1 to the right, that's its new vertex. The compressions don't matter because multiplying by 0 is 0. Just the additions matter. So that should be its new vertex, 1 comma minus 6. It's not reflected at all, so 1 comma minus 6, it's going to 1 comma minus 6 is going to kind of look like that and like that. And this 3 and this 3 will make it be really thin. So let's see if I can do that. So there we go. There's the new vertex. And there's some other points too. Probably won't get clean points. Let's see some clean points here. There you go. There's some clean points. Very thin. Okay, I'm going to keep going. Okay, so this is some parabola work. So I can tell you that those dictate when x is 2 in here, the whole thing becomes 0. So that's the x-axis. So there's 2 comma 0. And when x is minus 5, this becomes 0 and the whole thing becomes 0. So that means minus 5 comma 0 is right there. There's no negative or positive here, so it's a positive, so it's upward facing. I can tell you that, so it's negative 5 comma 0, 2 comma 0. I can also tell you the axis of symmetry will be halfway between that. They're 7 apart, so 3.5 here. So the axis of symmetry will be minus 1.5. I could plug that into the equation and come up with the asymptote if I wanted to. So that's the answer to that one. So what happens when I multiply this by minus a third? Okay, so you cannot really... Let's come up with the vertex. So I'm going to take... I know the vertex is minus 1.5. So when I take minus 1.5 minus 2, I get minus 3.5. And when I take minus 1.5 here and add 5, I get 3.5. So that means my vertex is negative 12.25. So this will be my vertex. Which means my vertex formula will look like this. Which means that's how it's been translated already. To prove this, you can just put the factored form in here. And you can put the vertex form. And you'll discover the same graph. Now, what you do for all the x values, you can also come up with some standards here, right? You can come up with a table of content like this. And actually, you know what? You could just take the main roots. So here's the main roots. When x was 2, y was 0. When x is 5, minus 5, y was 0. So when I multiply this, this is taking all your x values, multiply them in the negative, and then multiplying them by 3. Or sorry, not by 3. Yeah, multiplying by 3 because this is a third. So, and how do I know that's an x value? Because if it was out here, that would be a y value. So if I multiply this by negative 3, I get negative 6, 0. And if I multiply this by negative 3, I get plus 15, 0, which would put their asymptote halfway between that, which is 21, which is 11 and a, or 10 and a half, so it's at 4.5 is the vertex of that one. If I wanted to do it to this formula, I would just put a big old inside this bracket, negative a third. Let's see if that works. Let's call this g of x. And we'll call h of x equals to g negative a third x. Now let's see if I got my new, there's my new asymptotes. There's my new vertex. Same depth because there was no stretch, vertical stretch or anything. Now, how would I put that into the actual equation? Here's what the actual equation would look like. So I have to multiply. I would just take the same equation, put a negative a third in front of it, put x plus 1.5, square that, and then minus 12.25. And my blue and my, oh, I got it wrong. Let's see. Negative a third times all my x values squared that should have worked, I think. Why didn't it? let's see. Do I have to multiply it through to everything? I think I might have to multiply it through to everything. So it might have to be this, actually. No, it should still have worked. Okay, let's see what happened there. I'm just having a little brain fart and just too tired. So this is supposed to be applied to all of that. But that's clearly not it. That's interesting. So I'll have to figure out what I'm doing there. What I'm doing wrong there. Clearly doing something wrong. But that's okay. I'm just having a brain fart. We'll just stick with that. But that should have... That should have done all of it. Anyway, I accomplished what I wanted to do. Okay, what about this one? This is outside, so I simply multiply all my y values by that. I'm going to get the same this, but I should really know my vertex, so because these just stay the same. So when I multiply my vertex by -4, this whole thing flips upside down, and it becomes positive 24.5, positive 24.5 becomes 49, positive 49. So it's -1.5, positive 49, and goes through the same things. Let's see if that's true. Yeah, so oh, you know what that I've got wrong? No, I got it right. Yeah. So there you go. And look, it goes through the same original values. And then this last one, I have to multiply all the x values by -1 and then subtract 2. So they become the original ones were -5, 0 and 2, 0. So when I multiply by negative, it becomes +5. And then I've got to subtract 2. And the other one becomes -2 and add 2, 0. So I've got 0, 0. And then really, I should find the asymptote of this. So if I multiply the -1.5 by negative, it becomes 1.5. And then when I subtract 2, it becomes -0.5, 12.25. And it's reflected in the y-axis. Let's see if that's true. Minus an x plus 2. All right, let's see. Yep. There's -0.5, and there's the asymptotes. Actually, I got that one wrong. I added 2 instead of subtracting 2 because I'm getting tired. So I added 2 to the -2 instead of 0. That should be -4. It should have been subtracting 2. But I got everything else right. So you can see as you get tired, it gets worse. List the steps you would take to sketch the graph in the form that when fx paragraph you have studied in the chapter. Discuss the rules of A. I would pretty much apply y first because it's easier, and then x. Let's try these last two. They're extending, so I don't know. I don't like answering the extending ones because sometimes they're just a little bit too much. The graphs are shown. Determine a combination that could produce the second from the first. Okay. And then a second equation. So, here's y is equal to x squared. So first of all, there's a reflection in the x-axis. So there's a minus in front of that a. Second of all, the normal a is that, 0. So even no matter what I multiply it for by, it's going to be 0. But then it's been raised by up to 2. This is 2. So that means there's a plus 2 over here at the d or whatever it is. And I still don't know what the a is, if it's just minus or not. Let's just leave it as minus. The x value, 0, has gone over to minus 6. So I can say x plus 6. Now there's more information here. For instance, it goes through what appears to be minus 90 and 50, but not quite too accurate, or minus 30. That's not too quite accurate. So if I was going to do this, I would just sort of say y is equal to minus 1 x plus 6 squared, and then add 2. But I would need a couple bits more data. For instance, I would just leave that as a, and then I would find a value for, let's see if there's a clear-cut value down here. This looks right here like minus 7 comma 0. So then I'm going to put in a 0 for x and a minus 7 for y, and I'm going to leave that as a plus 2. So I get minus, I'll show you what I'm doing here. Why am I doing that? So I know it's a minus a, I just don't know what a is. I know it's plus 6 to get the 6 over. And I know it's 2 up to get the y up. So I just don't know the a. So I'm going to take the basic formula, y is equal to a. I'm going to just leave it like a, but I know it's x plus 6 because it moves to the left 6 squared, right? And I know it's plus 2 because it's gone up. Then I can see a clear point on the graph, which is right there, 0 comma minus 7. So I'm going to replace my y with minus 7. I'm going to leave my a, and I'm going to replace my x with 0 plus 6 squared. So I'll just write it like that. Plus 2 minus 7 is equal to a. 6 squared. What's 6 squared? 36. Plus 2. Subtract 2 from both sides. Divide. So I get, what's 9 over 36? 18. They both can be divided by 9. I get minus 1 over 4. So that means I believe the equation for this thing should be y is equal to negative 1/4, which faces downwards, x plus 6 squared plus 2. All right, let's see if that's true. Okay, so it passes through 0 comma minus 7. Doesn't quite have the x-intercepts that are implied. But it's close. That's about minus 9. And yeah, that's close to minus 9. And that's close to minus 3, but not quite. And that's close to minus 3, not quite. Goes through 0 comma 7. It has the vertex that I wanted. And just to compare, there. Yep. So, I mean, based on the limited data, that looks pretty accurate. Compare the graphs and domains of this and this. How are they alike? How are they different? Develop a procedure to obtain the graph of g of x from the graph of f of x. Well, they're inverse. So whenever you want your thing to do an inverse, here's f of x, or let's just say y is equal to x squared. Swap the x's and the y's. There's the actual inverse. Here's the square root function. You can see the square root function is just the top half of the inverse. Interestingly enough, the inverse of the square root function is only half of the parabola, which makes sense. But the inverse of the parabola is two sides of the square root function. How are they? Their domains, they're swapped. So the interesting thing about inverses is their domains and ranges swap as well, which makes sense because we're just swapping x and y. So that's how they're related. And I think that's it.